You know that feeling when a bus suddenly stops and you kind of lurch forward? Or have you ever watched a rocket launch and just wondered, how does that work? Well, it turns out none of this is random, not at all. It's all following a strict but actually pretty simple set of rules that governs, well, everything.
I mean, really, why does your hand hurt so much if you punch a wall? Or why do you fly forward when a car slams on its brakes? It all feels like common sense, right? But underneath that common sense is a fundamental code, a set of instructions for how everything in the universe is allowed to move.
That's right, the entire universe is playing by a very specific set of rules. I'm talking from a giant planet orbiting the sun all the way down to a soccer ball flying towards a goal. Everything follows the exact same rulebook. And you know what the best part is? It's a really, really short book.
How short? Just 3 rules. That's it. 3 core principles that explain all of it. And once you really get them, you'll start to see the hidden physics engine running behind absolutely everything you do.
So this rulebook, it was actually written down over 300 years ago by none other than Sir Isaac Newton. And it's easy for us to take this stuff for granted now. But back then, his laws of motion were completely revolutionary. They gave us a whole new way of understanding the universe. And here's the thing, whether you're an astronaut floating in space or just sitting on your couch listening to this, you are being governed by these rules right now.
All right, let's dive in. Rule number 1. This one is all about the universe's natural laziness, its tendency to resist any kind of change. Physicists have a fancier name for it, of course, the law of inertia.
Okay, so here's the official textbook definition. An object at rest stays at rest, and an object in motion stays in motion with the same speed and in the same direction, unless it's acted upon by an unbalanced force. Basically, things just keep on doing what they're doing.
But here's a much easier way to think about it. Just think of objects as being lazy. Seriously, they want to keep doing whatever they're already doing. If an object is sitting still, it wants to stay sitting still. If it's cruising along, it wants to keep cruising along. They just resist change.
Okay, let's go back to that bus example. Picture it. The bus is moving at 40 kilometers an hour. Now, because you're on the bus, you are also moving at 40 kilometers an hour. Suddenly, the driver hits the brakes. The bus itself is being acted on by an outside force, the brakes, so it stops. But your body? Oh no, your body's inertia means it wants to keep right on going at 40 kph, and that's that lurch. That's why you fly forward.
And that right there is exactly why seatbelts are so incredibly important. The seatbelt is that unbalanced force we were talking about. It's designed to act on you, to stop your lazy body safely right along with the car. It stops your inertia from sending you through the windshield.
Okay, so that's rule 1. Now let's move on to rule 2. If the first law is all about resisting change, then the second law is all about what it actually takes to cause that change. And yeah, this is where we get into a little bit of math. So Newton's big aha moment was this. He realized that how much an object accelerates depends on just 2 things. And by the way, when we say accelerate, we don't just mean speed up. It's any change in motion, slowing down, turning, anything. So acceleration depends on 1, how hard you push it, that's the force, and 2, how much stuff it's made of, that's its mass. And this simple idea gives us what is probably the most famous equation in all of physics, force equals mass times acceleration. You know it, F equals ma. It's so simple, so elegant, but it is incredibly powerful. It really unlocks how the physical world works. Here's a super simple way to think about it. Imagine pushing an empty shopping cart. It has a pretty low mass, right? So it takes just a little bit of force to get it going. Now, imagine trying to push a car. It's got a huge mass. To get that car moving at the same acceleration as the shopping cart, you'd need a massive amount of force. It's that simple, really. More mass requires more force.
All right, that brings us to our third and final rule. And this one is about a deep universal truth of the cosmos. There is always a pushback. You might know it as the law of action and reaction.
Oh, you've definitely heard this one before. For every action, there is an equal and opposite reaction. But what does that really mean? It means that forces never exist alone. They always come in pairs. You literally cannot touch something without it touching you back with the exact same amount of force.
This is the secret to how a rocket works. A lot of people think it's pushing off the ground or the air, but that's not it. A rocket's engine throws hot gas downwards with incredible violence. That's the action.
And in return, that gas pushes the rocket upwards with equal violence. That's the reaction. And that's what lifts the whole thing into space.
In fact, you don't need a rocket to see this law. You use it with every single step you take. Think about it. When you walk, your foot pushes the ground backward. That's the action. The ground's reaction? It pushes your foot and you forward. Walking is just a constant little dance of action and reaction.
So there they are, the 3 fundamental rules that run the entire show, that govern all motion in the universe. Let's do a super quick recap just to lock it all in.
Okay, so Rule 1, the law of inertia. Basically, objects just keep doing what they're already doing. They're lazy. Rule 2, F equals ma. Or in simple terms, pushing heavy stuff is harder than pushing light stuff. And Rule 3, action-reaction. You push something, it pushes you back. Every time. So the next time you kick a soccer ball, or feel yourself getting pushed back into your seat as a car speeds up, or even just take a simple walk, take a second to remember, you're not just moving. You are interacting with the fundamental rules of reality. You're doing physics. And that leaves us with one last, kind of mind-bending question to chew on. If every single action has an equal and opposite reaction, then how does anything ever actually move?